steam condenser is a very important device in the Rankine cycle. The Rankine cycle basically consists of the boiler, a steam turbine, condenser. The water from the hot well is fed through the pump to the boiler where it is converted into steam. High pressure steam is passed to the turbine, and here we have a low pressure steam. In condenser we get a phase change, and then the water from this in the liquid form called as condensate is given back to the hot well. The work is developed by the turbine. Here we have wet steam. The wet steam is converted into condensate. The given Rankine cycle can be represented on PV diagram. Here 1 to 2 is the constant pressure heating process in a boiler. 2 to 3 is a isotropic expansion in steam turbine, and 3 to 4 is the heat rejection process in condenser. 4 to 1 is again a feedback process. If the condenser is not used, then the expansion for maximum work is up to atmospheric pressure. The steam, if it is exhausted up to atmosphere, we can give it to this, and in that case the work will be equals to 1, 2, 3, 4, that is this area, from P1 to the boiler pressure to atmospheric pressure. If we use the condenser, then it is possible to expand this below the atmosphere, and in that case the additional area is represented by 3 to 4 This pressure is lower than atmosphere. In that case the work developed by turbine will be 1, 2, 3 to 4 and we find here that this work is more as compared to the original work 1, 2, 3, 4 because of this additional. So this is the extra work produced in the steam turbine because of condenser. Therefore condenser are the essential and the important parts of steam turbine power plant. Since we are keeping the same heat transfer, same heat supply to the boiler, work done is increased. Therefore there is an increase in the turbine efficiency. So here the condenser improves the efficiency of the power plant by decreasing the exhaust pressure of the steam below the atmosphere. Another advantage of the condenser is that the steam condensed may be recovered to the steam condensed here may be recovered to provide a good source of feed water to the boiler, and this reduces the overall cost of the feed power plant. Normally we use the water from the stored water, which is to be chemically treated. If we use the same water again and again from the condenser, it will save the cost of water treatment. The pressure inside the condenser is maintained below atmosphere by condensing the steam with the circulation of cold water. The quantity of the water circulated through the condenser and temperature of water decides the vacuum which can be maintained in the following graph represents the effect of mass flow rate on the condenser volume with the cooling water temperature, and here we have a condenser vacuum and the mass flow rate of water per kg of steam, that is the amount of water circulated per kg of steam through the condenser. It is observed that here that if the temperature of the cooling water is very low, the vacuum can be maintained very high up to 750 mm of Hg. As the temperature will go on increasing, there is a drastic drop in the vacuum of the condenser. Therefore, if we use the high temperature of water, the vacuum will be equal to around 700 mm of Hg, and because of that the work developed by the turbine will be reduced. If we observe the effect of mass flow rate of water per kg of steam on the condenser vacuum, what we observed is that as we increase the mass flow rate of water, the amount of heat removed from the condenser is very high, thereby the pressure will drop drastically. So if we maintain around 80 kg of water per kg of steam, we can get a vacuum of 750 around, and if we have a ratio of 40, then we can maintain a vacuum of around 700 mm. Before we start a discussion about the condenser, let me have some initial idea about the relation between the gauge pressure, atmospheric pressure and absolute pressure. If we have a vertical axis here representing the pressure, this one represents the complete vacuum or absolute zero, which is possible at 0 Kelvin or minus 273 degrees Celsius. Above that we mark here one level, that is equals to the local atmospheric pressure, which can be measured by the barometer, and we treat this local atmospheric pressure as a zero gauge. That is the reference value for measuring the positive gauge or negative gauge. If we measure the pressure above this, we will get here the positive gauge value. Any pressure is measured below the local atmosphere is basically called as vacuum or is treated as negative gauge pressure. If we measure the quantity from this reference above this one, then it is called as absolute pressure. So for point B, if we measure the pressure from this side, we get absolute pressure, which is equals to the atmospheric pressure minus this value, that is P atmospheric minus P gauge. If any pressure is measured above the local atmospheric, that is the for positive gauge pressure from this reference. So for this point A, P absolute is equals to the atmospheric pressure plus the gauge pressure. So you have to use negative sign if you are below the local atmosphere, and you have to use the positive sign if you are measuring above the local atmosphere. We know that atmospheric pressure, particularly local, is measured by using a barometer. Hence atmospheric pressure is also called as barometric pressure. The standard value is 760 mm of Hg is equals to 1.01325. 760 mm of Hg is 1.01325 bar, not kilopascal. Approximately 750 mm of Hg is equals to 1 bar. The standard atmospheric pressure is 760 mm of Hg, which is equals to 1.01325 bar. In case of condenser, normally two terms are used. One is vacuum in the condenser, and the vacuum that we are using in the condenser is to be corrected vacuum in condenser with respect to the standard atmospheric pressure. So normally vacuum is measured with respect to local atmospheric pressure, and if this vacuum is referred with reference to the standard atmospheric, it is called as corrected vacuum in the condenser. We have a same diagram here. This is a zero pressure. 760 mm of Hg is the standard atmospheric pressure. Let assume that the local atmospheric pressure is less than P atmospheric. Local atmospheric pressure can be greater than standard atmospheric pressure also. For the present case, we will assume that the local atmospheric pressure P atmospheric is less than 760 mm of Hg. In the problem, if you are given any vacuum, then that vacuum is always treated with the local atmosphere. So using that value, you have to move downward because vacuum is always a negative quantity. And if you measure this point pressure with reference to this one, it is called as absolute pressure in the condenser. We refer this as P mix. So P mix is the absolute pressure in the condenser, which is equals to the atmospheric pressure minus gauge pressure, or P atmospheric minus P vacuum. P mix is given by P local atmospheric minus P vacuum. If we try to measure the same value from the standard atmospheric, our P mix remains same. This is the reference value measured with reference to standard atmospheric is called as corrected vacuum, and we know that the P mix is not going to change. So this answer, this P mix, can be obtained as P standard atmospheric, that is value from this point to this point, minus this value, which is equals to same as P mix. So P mix can be given as P standard atmospheric minus P corrected is equals to 760 minus P corrected vacuum. Let's take one simple problem here. A vacuum of 68 cm of Hg was maintained in a condenser with a barometer reading of 75 cm of Hg. Find the corrected vacuum to a standard barometer reading of 76 cm of. So in the problem, we have given the vacuum pressure is equals to 680. 1 cm is 10 mm. So 680 mm of Hg. The local atmospheric pressure is equal to 75 cm, that equals to 750 mm of Hg, and the standard barometer is 760 mm of Hg. So P mixture is given by P local atmosphere minus P vacuum, which is equal to 650 minus 680. So 750 minus 680 is equal to 70 mm of Hg is the absolute pressure, is the P mix here. This P mix remains same from 760 minus corrected vacuum. So P mix equal to P standard atmosphere minus P corrected. But we already got the value of P mix is equal to 70, so we'll substitute here 70. Standard is 760, so corrected vacuum will be, the corrected vacuum with reference to the standard atmospheric pressure is 760 minus 70, that equal to 690 mm of Hg. We can convert this 690 using a standard conversion ratio. 690 divided by 760 into 1.0325 is approximately equal to 9.199 bar or 0.92 bar. In the condenser, normally we use the Dalton's law of partial pressure, because in the steam condenser we are using the steam and air. So we have to apply the Dalton's law of partial pressure in the case of condenser. The Dalton's law basically deals with the mixture of gases, which consists of number of phases. Suppose we have a law, the law states that total pressure exerted by a mixture of gases at same temperature and pressure is equal to the individual partial pressures of the constituents of mixture. Suppose we have a gas has two constituents, gas A and gas B, then according to the Dalton's law of partial pressure, the total pressure due to mixture, that is P mix, is the pressure due to gas A and the pressure due to gas B. The water is circulated in a steam power plant, contains water and the dissolved air. During the boiler operation and the steam turbine passage, they act as a homogeneous mixtures of vapor and air. In the condenser, during the condensation, this air is liberated from the steam and therefore the condenser volume is filled by both steam and air. Both the air and the steam exert the pressure in the condenser. This total pressure is called as P mix. The entire condenser volume is filled with the mixture of the steam plus air. They are the same volume and the same temperature, and therefore we can apply the Dalton's law of partial pressure in the case of condenser. So according to Dalton's law of partial pressure, the total pressure in the condenser is equal to P mix is equal to partial pressure of air plus partial pressure of steam. Partial pressure of steam we can obtain from the temperature given of the condenser from the steam table. We also know that the total pressure in the condenser P mix is equals to P atmospheric plus P vacuum. So either they can provide you data of P atmospheric or they can provide you the data of P vacuum. In P vacuum you have to take the negative value, you have to add this and you can find out P mix. Once we know the P mix, we can find out partial pressure of air. So the actual vacuum is equal to this term, that is PV of air, PV of P vacuum is equal to P atmospheric minus P mix, but P mix is already equals to P air plus P steam, so P vacuum equal to P atmospheric minus sum of P steam plus P of partial pressure of steam plus partial pressure of air. This quantity can be increased if this value will be equals to 0. So ideally we can say that the ideal vacuum will be maximum if the partial pressure of air is equals to 0. From this we define the term called as condenser vacuum efficiency of a condenser. So P ideal is equal to P atmospheric minus P steam. P ideal of the vacuum is equal to P steam, atmospheric pressure minus partial pressure of steam. So vacuum efficiency is defined as the ratio of actual vacuum upon ideal vacuum. If we substitute for P actual vacuum, that equals to P atmospheric minus P mix, and ideal vacuum is equal to P atmospheric minus P of steam. So this is P of steam, and this mixture is consist of both, that is a PS plus PA, where PS is the partial pressure of air and PA is the partial pressure of. If there is no leakage through the glands or packing, then the P mixture will be equals to PS plus PA. So PA will be equal to 0 because there is no mass of air in the condenser. So P minimum will be equals to, so P minimum will be equal to PS. In that case, the vacuum efficiency will be equal to 100%. It indicates that there is no leakage of air inside the condenser. Factors which will affect the vacuum efficiency is that number 1 is the air leakage. As the air leakage will increase, the mass of air will increase, therefore partial pressure of air will increase, and once the partial pressure of air will increase, the vacuum efficiency will going to decrease due to increase in the partial pressure of vapor. And number 2, the vacuum efficiency decreases with the increase in the barometric pressure. So there are two parameters which controls the vacuum efficiency. We want the highest possible value. The third important parameter is the cooling water flow rate. If the cooling water flow rate is not sufficient, then the pressure in the condenser will increase and subsequently it will reduces the vacuum efficiency. Once we are now familiar with the steam condenser with the Dalton's law of partial pressure and the vacuum efficiency, let's do some basic thermodynamic analysis of the steam condenser. Consider here one spherical shell, that is a condenser having volume equals to V. This complete volume is filled with the volume is both by steam and the air. We cannot separate air and steam here. That is a homogeneous mixture. So what we can say is that the total volume V is also the volume of air plus volume of steam. For simple thermodynamic analysis, first of all we neglect the mass of air, and in practical situation also the mass of air is very small as compared to steam. So we can neglect the mass of air to compute the mass of steam. The wet steam from turbine passes through the shell side and the condensate is collected from the bottom side. Let m dot s represent the mass flow rate of water or condensate kg per second. At inlet to the condenser, the point number 1, we will say H1 is the enthalpy of steam at inlet. Depending upon the condition of steam at the turbine outlet, we have H1 equal to HF plus X HFG when the steam is wet and Hg when the steam is dry. So at exit we have a condensate, which is the liquid water. So let's say the T2 is the temperature of condensate. Number of times we will denote this by Tc also. C for condensate. H2 will be the enthalpy of water at Tc, which will be equals to Hf at Tc. So steam is flowing with the mass flow rate of Ms. H1 and H2 is the change in enthalpy. So Q is equals to the heat rejected by the steam is the product of mass multiplied by change in enthalpy H1 minus H2. The heat rejected by the steam is carried away by cooling water. So cooling water is flowing through this with a number of tubes. Let m dot w represent the mass flow rate of cooling water and corresponding inlet temperature is TWI, and let the hot water temperature is TWO. Mass flow rate of water is in kg per second, same as the steam. TW is the water temperature and TW2 is the water. TW is the water temperature and TWO is the water temperature outlet. The heat gained by cold water, which is rejected by the steam, is Q is equal to m dot w into CPW into TWO minus TWI. CPW you can take as a standard value is 4.186 kilojoule per kg per Kelvin. If we balance this one, we can find out the quantity of heat required, quantity of the water required for the above cooling effect. If we draw the temperature versus the length diagram, what we observe is that if there is no phase change process, that steam temperature will remain constant. So we have a dome here, and in the dome, whenever the phase change takes place from this point to this point, in a TS plot, the temperature versus entropy plot, the temperature remain constant and is equals to Tsat. So this temperature is Tc is equal to Tsat at the corresponding P mix. The water is entering from the temperature TWI to TWO. So actual rise in temperature of the water is TWO minus TW. The maximum possible temperature can be possible if the outlet temperature is equals to the Tsat or the T2 of the condenser. So delta maximum rise in the case of condenser will be, so maximum temperature rise is possible in the case of ideal situation. The maximum temperature is Tsat minus TWI and the actual is TWO minus TWI. This is just a ideal situation. Since we have a rise equals to actual rise and maximum rise, we will define the condenser efficiency as actual rise in the temperature of water upon maximum possible rise. Actual rise is TWO minus TWI, maximum rise is Tsat minus TWI. This efficiency is very high, around 90 to 90. The calculation for mass of steam and air. So we have a same shell, V is the volume of air, V is the volume of the condenser, and this volume is entirely filled by both. So volume of air is same as the volume of steam. We know that P mix is equal to actual pressure in condenser, which is equal to atmospheric pressure minus the vacuum is all, whenever we have vacuum we have to use minus sign, and the same pressure is also equals to the steam of pressure plus partial pressure of air by using the Dalton's law. If we have given the Tsat of the condenser, then we can find out from steam table the partial pressure of steam. Once we know the partial pressure of steam and the total pressure in the condenser, we are able to find out partial pressure. So from equation number 2, the partial pressure of air is P mix minus P steam. The mass of the steam in the condenser is given by volume divided by the specific volume Vg. If it is wet, you have to use X into. Take care for the steam that since the steam is not ideal gas, do not use the equation PV equal to MRD. Rather use the equation V upon Vg. But air can be very well modeled as an ideal gas, and we can use this equation PV equal to MRT, where M is equals to PV upon RT. So when you are finding the mass of air, you have to take the partial pressure of air and the temperature of the condenser. The volume is remain same, R is the gas constant, which is normally equals to 287 joules per kg per Kelvin in case of. Now from the knowledge of the Dalton's law of partial pressure, the mass of steam condensed, vacuum efficiency, then condenser efficiency. Let's solve some basic problem based on condenser in the next few lectures.